Hello, everybody, and thank you for joining us in today's webinar, PSIM on Autopilot, exploring different ways to automate your power electronics simulations. My name is Nikos Dimitrakopoulos, and I work as a senior solution engineer at Altair Engineering from our offices in Athens, Greece. My background is in electrical engineering and power electronics, and I'm part of the technical team that supports and promotes PSIM globally, especially when it comes to power conversion workflows. Today's webinar will not be a step-by-step guide on how to script PSIM itself. Instead, I will try to provide an overview of what's possible. To be more specific, I hope that by the end of this session, we'll have a clear understanding of all the possible ways to automate PSIM in order to save time, build automated routines, and be able to fully explore the design space of your designs in order to optimize selected key performance indicators or KPIs. So I will proceed with the full screen. And before discussing the agenda, I want to clarify that this webinar will be recorded and the recording will be uploaded to YouTube, and that the slides and simulation files and examples you will see today will be shared probably with a PSIM article in our Altair community. Now, before moving on with the agenda, I think we have prepared a poll for all the attendees, and maybe we should start it right now in order to give some time for people who are still joining us. Albert, are you able to provide the questions of the poll? Not sure how this works. Okay, so let's move on. Today's agenda. We will start with an introduction. I will briefly touch the topic of Altair's acquisition by Siemens, and we will also briefly discuss the different options of automating PSIM. There are four main methods. The first one is the C language scripting. This is the legacy standard. This is the how PSIM was scripted until now, until the acquisition by Altair like 3 years ago. And then we added other methods as well. The first one is the Compose OML method, which is a matrix-based language. For those of you who have used MATLAB or Octave in the past, you will find a lot of similarities. You will find scripting with Compose very easy. Then there is Python, which is, of course, modern and widely adopted, especially by young engineers. And finally, we have HyperStudy, which is a code-free platform for design exploration and optimization. So each one of the methods will have a different section in today's session. Moving on with the introduction, in case you haven't heard, Altair was acquired by Siemens in March 2025. That makes it 6 months now. Wow, time sure flies. I don't have anything really new to add to this, except from the fact that still things are moving on. For example, I got my Siemens email. We are still waiting on the specifics, though, on how the tool will be integrated, and we expect more clear, let's say, integration and information around January. So the current history of PSIM is the following. So the company PowerSim was founded in the early 2000s. I believe the PSIM solver was already existed. It was developed by Dr. Hua Jin, who is still working with us in Altair. He's part of our development team. So that makes PSIM's history close to being 30 years now. I think this really shows that this is a well-established tool in the market for power electronic simulations. Then the company PSIM was acquired by Altair 3 years ago in early 2022, and this brought a lot of integrations and additional features to PSIM. And we hope that with the acquisition of Altair by Siemens now in March 2025, this will bring even more potential to the tool and helping us transition from the 1D domain to multi-physics approaches and having integrations with multi-physics tools and data analytics and AI tools. So moving on, there are four main scripting methods to automate, or rather, there are four methods to automate PSIM, and three of them are scripting methods, and one of them is a code-free approach. I will start with C scripting, which is the oldest. It's the legacy method of automating PSIM. The advantages of C scripting is that it's really fast, both in execution time, but also in the way that it works. You just open PSIM and there is a script tool, you can directly script there. There is no need to download any dependencies, and there is no communication with external tools or Python, which can bring latencies. So it's the fastest way, but it has a complex syntax. Of course, this is a matter of preference as well. But what we came to understand Altair support is that a lot of people nowadays, especially young engineers, don't really want to think about putting commas, putting the correct brackets, and having complex syntax when it comes to the if-else statements and the iterative loops and all that. They are used to working with much simpler languages, which we call scripting languages. And one very common one is MATLAB. Altair offers its own matrix-based syntax language, which is called OML. And basically, it comes with the environment of Compose. That means that you have to download the Altair called Compose, and there you can script with a matrix-based syntax. If you are familiar with MATLAB or Octave, this will be very, very easy for you. But the drawback is that you still have to download an additional tool. With the way the Altair licensing works, you don't really need to pay anything extra. This is included in the package because Altair doesn't sell licenses like the license of PSIM, for example. You have the Altair units, which is basically tokens. And if you have enough tokens to use PSIM, then you can already use Compose, for example. So you can directly go and download it. Then we have Python. Python is the newest scripting addition to automating PSIM. It's very popular, obviously. It's very easy to work. Everyone knows about Python. There is no need to download an extra tool or something. You still have to download Python, though. Let me say that if you download the Altair HyperWorks portfolio tools like HyperStudy, Python will automatically be downloaded. So for example, if you already have HyperStudy installed in your machine, you don't have to go and re-download Python from the official website. But some drawbacks is that we haven't completely incorporated all the features yet, or we have faced some issues which we expect to be fixed in version 2026 of PSIM. One example is the multi-thread simulations with the asimulate functions, but we will talk more about this later. And finally, we have HyperStudy, which is the scripting-free approach. HyperStudy is basically a separate tool. It's a platform. It's not a simulation tool. It's a platform that helps you automate PSIM simulation by just navigating to where the schematic is. You click a button, you have all the variables of your schematic in HyperStudy. You can put lower, upper bounds. You can put tolerances and make them follow a statistical distribution, for example. And then there are dedicated algorithms and post-process tools inside HyperStudy to help you explore the design space or apply optimization routines from the operation research area of mathematics, and you can even build static reduced order models with PSIM trained data. So HyperStudy handles the inputs outputs very efficiently, which is very important when it comes to automation, and it makes it super easy to debug. So in case something is wrong or you see some results that doesn't make sense, then it's very easy with HyperStudy to navigate directly to that example, open it and test it and see what it's wrong. Whereas with scripting languages, you have to be careful on how you save the results. You have to create separate folders maybe and give them specific names. And finally, you have post-process tools inside HyperStudy directly, like scatter plots, linear effects plots, Pareto plots, and all that are directly there. You don't have to script them in order to view the results and compare the data. The drawback is that as Compose, you need to download another tool, which is HyperStudy, and that it has a learning curve, that it's a platform. In my opinion, it can elevate an electronics engineer by a lot. It gives you functionalities that are directly ready to use for you without you having like a master's in data analytics or optimization routines and all that. So it really makes you a stronger engineer, but you still have to put some time into it in order to understand how it works. Now, I will move on with the first method of scripting, which is the C language, which is the legacy way of automating PSIM. For every section, the first thing I will do is I will provide some tutorial material or learning material, because as I said, this webinar will not be a step-by-step guide on how to automate PSIM. So in all of the sections, I also provide a QR code, which you can directly scan and navigate to the dedicated tutorials. So for the C scripting, there is an introduction tutorial, which you can find in YouTube. And there are also other ways of finding information inside PSIM. I will spend some time to directly show you that because I think it's very important. So I will open PSIM. And first of all, I want you to know about this help section here, and especially the help index section, which I believe is very useful. So in this section, first of all, you can type things down. For example, if I write Python, I can view tutorials, I can view Python functions, which I can directly click on them and see how they work. But in the left pane here, there is a dedicated section for the script help. So if I go to the script help, these are all the script, the legacy functions that you can use, and they're divided in computational functions, operators, control functions, and of course the simulation functions, which are very important. So you can always use this help browser, that's for sure. And then there is also a tutorial, a PDF tutorial, if you navigate to help, tutorials, how to use script functions.pdf, which is open right here. And it provides a getting started procedure, and also it's a rather long tutorial, so it contains a lot of information when it comes to the legacy scripting way. So how does it actually work? So of course you can see all the functions and how they are, like the list of inputs that you need to use and all that, but how does it actually work? So you can navigate to this script menu right here and click script tool. And then this window appears and you can type a script in C language and use the functions that you will find in the help menu. Or if you don't want to start from scratch, you can go to File, Search Examples. This is another place I often go. And this is why I show you. This list of examples is actually very nice. And I use PSIM every day and I still learn a lot out of all these examples. And whenever I want to start new applications, I always check there in case there is something. So for the script, there's a dedicated list of several scripts that I can directly run. I chose 3 simple examples for today's session. So I will first start with a thermal example. The thermal example contains a simulation, so a schematic that is attached to this script. And then there is also the script. So let me open the script. So this is how the script tool looks like. Let me say that there is a nice option which is called check its syntax. So you can press that option and see if the syntax passes. You see semicolons here, but in fact, the simulation can work without semicolons because this is still C, but it's a bit more convenient. It's not that strict in this case of PSIM scripting. So if I click run check syntax, this still passes and I'm able to run the script. Before running it, let me describe briefly what happens here. So in this simulation, what I want to do is I want to compare the losses of different MOSFETs in a very simple buck converter topology. Of course, it doesn't have to be a buck converter, but since it's the simplest topology that everyone knows, you will see a lot of buck converter examples today. I don't want you to focus on the topology though, just the methodology. So we have a device list. So you have different device names here, as strings that are saved in a list with brackets. And then what I want you to notice is the simulate function. So the core of what will happen is here in the simulate function. The only input that is needed for this function always is the schematic file. So the function needs to know where to find the schematic. In this case, you use this option like get local in order to get the file path of the script, and then you add the actual schematic name to it in order to have the complete file path, and this is the complete file path you pass into the simulation. The other inputs are optional. I will mention this information once because it's the same for all scripting options. So in all scripting options, no matter if it's in C or Python or Compose or ML, you will see a simulate function. The necessary inputs will be the schematic because the function needs to know what schematic to run. And then optionally, you can also define how the output file will look like. So you can define the file path of where to save the results and the file name. And preferably, you want to save each result with a different name in order to be able to compare between them at the end. So, and then you also pass the parameters of the simulation. So in this case, I will click run. And then I got a message that the PSIM script is complete. Now, what happened? PSIM ran, how many there are? 1, 2, 3, 4, 5, 6 simulations subsequently, and calculated the steady state losses for these simulations. Let me navigate to the results. So you can plot the results inside the script tool, or you can also save them and save them in a TXT file like we did here and use them later. So I'm looking for the TXT file as we speak. So examples, script, thermal. Okay, here it is. So this is the output of this simulation. And this is what we do actually here. We define these headers, and then we basically build our way into a TXT that will give us the total losses and the conduction and switching losses for each device. Now, this is a very simple example. I will move on to the next one, which is basically an AC sweep. Again, I will close this and I will move to the script examples right here. I will even close the simulation and I will open the first one, the AC sweep one. So I can see that the file name that is being called here is called back.acsweep.psim schematic. This file should be somewhere in here. Let me open it as well. It's inside the files. Okay, here it is. So once I run this simulation, I directly get the Bode plots for this simple buck converter. Now, this may seem simple, but due to the fact that the Bode plots are actually a compilation of time domain simulation, what just happened is that PSIM run 51 different simulations in 3 seconds in order to compile the results into these body plots. So you may notice that in the x-axis there is frequency. So what this means is that we introduce a perturbation right here, which has a different frequency each time, and we measure its effects on the amplitude and the phase of the output voltage, and this is how we compile the results into these body plots. I want to show you this example because I want to be cognizant that not only you can save the results in an SMB file, as it's shown here in this simulate function, but this function also returns the graphs which can be used internally in the script tool. So you can use the plot functions from inside the script tool and parse these graphs object that is being returned from the simulate function, and you can actually plot things that are inside this graphs object directly from within the script tool. And the final example I prepared for you today for the C scripting is the asimulate and parameter sweep, again for a buck converter. So the simulation in play is this one. And the script I'm going to use, it's the parameter sweep asimulate. This is all of these results. You can directly run them yourself if you navigate to File, Search Examples. So I will click Run Script. And what is different in this case is that instead of using the simulate function, I'm using the asimulate function, which basically means I'm running simulations in parallel in a multi-thread approach this way. So when you use the asimulate function, you have to be careful and you have to always set up the wait function as well, because you don't want to overwhelm the computer resources by trying to run all of the different scenarios in one place. So the way this simulation works, we have an inductance, a filter inductance, and we have 50 different values for it, starting from 1 milli to 50 milli with a 1 milli step. So there are 50 different points, and we run them by batch running them in combinations of 8 simulation each time. So, and then we plot the results. So this is a parameter sweep of the inductance, which is in the x-axis, and this is the simulation outputs in the y-axis. So when I run this example, I noticed something that was not making too much sense, and this is something I wanted to discuss with you. So the inductance is getting larger, but I see that the final value of the output voltage is getting smaller, which to me didn't make sense because I'm always using a 50% duty cycle. And in these cases is where you need to start debugging, for example, to understand why am I getting this result. So what I can try is I can try putting this value like 50 milli and running the simulation and seeing the results. So the results are instant, and here are the results. So the reason why the voltage is dropping is because when the inductance gets larger, the transient of reaching steady state is also slower. So with a constant total time here, the simulation doesn't have enough time to reach steady state. So the simulation finishes, it takes the last value of the voltage, which is lower than 50. It should be 50 because the input voltage is 100 and we have a 50% duty cycle, but the simulation finishes earlier. And this is where the steady state block comes handy. And I wanted to show you this block because it will be very useful to you when you try to automate PSIM. The way this block works, you put an input to it. If we're talking about DC-DC conversion, the frequency you should use here is the ripple frequency. If it's an AC signal, then it's the primary frequency of the AC signal. And then you define a relative tolerance error. And when this error is preserved for this number of cycles, then the simulation assumes that it has reached steady state and bypasses this total time option. So if I run this, if I make the total time much larger, in order to not cut down the simulation too early, and I run this again, I see that my simulation now stopped after it detected steady state, And this is much more, let's say, it is very useful for you when you run a lot of scenarios and you don't really know when the steady state will be actually hit. Now, let's run this example again. I will put the variable L1. Of course, you have to parameterize this, right? I'm using a parameter L1 inside the simulate, and this has to be a parameter in order for the script to work. So I will run the script again. And these are the results. So I still keep seeing weird results, which led me to another observation that this circuit is actually what starts measuring the output, and you have to put a start measure flag here, which is a bit inconvenient again because you don't really know when you want to start comparing and measuring the results from. And I mention this because we will see later other approaches of how to do this with external functions, with Python syntax or OML syntax. Now, we are a bit behind on time, so let me continue with the other methods because there are other exciting things to talk about as well. Moving on, we'll talk about the Compose OML approach. This is a matrix-based language. So again, if you're familiar with MATLAB or Octave, this will seem very, very easy to you. There are dedicated tutorials in our Altair community regarding this method. I will let this slide for a few seconds in order for you to be able to scan if you want. The tutorials were made by my colleague Rafael, and there are both starter's guide and intermediate user's guide. When it comes to Compose, you need to follow a step. You need to navigate to Altair Marketplace and actually download Compose. So let me show you how this looks like. You need to navigate to altair1.com/marketplace, and then you will have a list of all the tools. You have to sign in with your Altair One account, and then you will have to click on the tool that you want to download. For example, this is PSIM. There is Compose here. There is HyperStudy here. You navigate to Compose, you go to software downloads, and you download the latest version, basically. As I said, if you have the units, the Altair units to use PSIM, then you can run Compose already. And in Compose, you will find almost all the functionalities that are covered in the legacy C scripting, including the parallel threading, the multi-threading assimulate function. So let's see how Compose looks like. I will open a back converter example, but I will open the script in Compose this time. So this is how Compose looks like. It may seem very familiar if you have used MATLAB or Octave in the past. Basically, this is where you script. There are the variable browser, and there is also the command box on the bottom. The syntax, I'm sure it will look very familiar to you. The way this works is that, again, you have to put parameters in the PSIM simulation, but disable the parameter file because these parameters will be parsed by the script. So you put some parameters, and then you can gather everything in an array. It's a struct, actually, inside Compose. So there are some minor differences in the sense that, okay, there is this PSIM assimulate function, and then this function needs a certain input. And then this certain input has a structure which you need to follow. So yeah, there are some small similarities, but the core idea is exactly the same. And the cool thing about Compose is that you can double click on this function, press F1, and you will get an online help menu giving you the information you need on how to define the actual function. So what are all the inputs and what are the expected outputs and so on. So the logic is the same. I can run this script again. What happens is that PSIM runs a bunch of simulations in parallel. It uses different capacitances, switching frequencies, loads, and input voltages. Or sorry, actually, these are fixed parameters. That's my bad. These are fixed parameters, and I'm just changing the filter inductance in this linear space. And then when the results are done, I can use a for loop and iterate between the results and actually plot them. You have typical functions like the figure, hold on, grid on, legend, X label, Y label. So as you can imagine, you have all the potential, and sky's the limit here, right? You can do anything you want. You can plot the results. You can post-process them in here. You can zoom in, check the overshoots. For example, to write your own overshoot functions or your rise time functions and so on. This is a very simple example of how you can use Compose. Now, moving on with the same idea of modern scripting, we have Python, which is the newest method you can use. There is a dedicated tutorial for Python. Again, you can scan this QR code in order to find it, or you can look for it in the Altair community, PSIM simulation using Python. And what I forgot to mention, both for Compose and Python, is that you can still view the help menu inside PSIM to get all the information you need for the commands. So if you navigate to PSIM, help, index, and you type compose, you will find the PSIM compose interface. So you will directly get here all the commands that you can use inside Compose in order to work with PSIM. The commands should always start with the word PSIM. So PSIM simulate, PSIMA simulate. This is a major difference between the script tool. And also there is the PSIM Python interface. Again, the same logic. You have all the different functionalities and functions that you can use with the help menu right here, inputs, outputs, and explanation of how this works. Additionally, for the Python, you can also navigate to the PSIM installation folder. So let me get there right away and show you. So 2025.1, there is a dedicated Python file. So if you go to this Python file, you will be able to find sample code. So dedicated examples that you can directly use from inside PSIM. And let me also say that if you create your own examples, you can go ahead and save them in this user-defined folder, again, within the PSIM simulation right here. And if you do that, then these examples will appear in this menu. So script, in this script menu, you will find them listed right here, and you can directly run them from within PSIM. Now, how does the Python link works? This is slightly different than Compose. The only dependency is that you need to have Python installed, and then you also need to install the PSIM Python API. So in order to do that, you have to navigate to Options, Set Path. At the bottom, you will find the Python folder option, and you have to define where your Python is installed. For example, I used the Python installation that came with HyperWorks 2025.1. And then you click Install PSIM API Py. You wait for a few seconds, and then you will get a message that the API was successfully installed. And then that's it. You're good to go. You can now use Python. You can now use Python either from Compose, because Compose can be used for OML syntax, but it also acts as a user-friendly IDE for Python syntax. So I can do a new option and write a Python file. You can also use R and TCL. So I can use a Python file here. I can write my Python code and can directly run it from Compose. I like using VS Code. So in this case, this is what I will show you. So I'm using VS Code to call PSIM. I'm running the demo of PSIMA simulate. You can find that in the Python folder saved in the PSIM installation folder, as I showed you earlier. And I want to show you that Python follows a slightly different syntax than Compose, but it's still the exact same logic. A difference is that you need to initiate the PSIM API Py, of course, in order for your script to understand the functions that you will be using from the API. Then you have to specify where your PSIM installation is and where is your schematic. This is basically what this first part of the example does. And then you have to call the PSIM function with the PSIM installation path, and this will create a PSIM object. And then everything you do after that is accessing this object, so this P1 object. For example, when I want to simulate something, I have to type p1.psim simulate. The first option here is how many simulations, threads I want to run in parallel, in this case 35. And then there is the sim data command. And here there are two different ways of setting up this sim data. The first one is a dictionary approach, and the other is the argument approach. I don't want to spend too much time into this. I don't want this to be a tutorial specifically for Python. You can find information in the PSIM help on what these functions are expecting as inputs. And if you have any questions, also please feel free to reach out to support. Let me say that this function has a problem right now in the latest version, and we are working on fixing it. We're expecting this to be fixed in version 2026, which will bring major updates both for the Python API and for HyperStudy. So please stay tuned and make sure to download version 2026 when it's released. Moving on, I wanted to state that there is a nice functionality of Python where you can save a schematic as Python code. So you can open a schematic, doesn't matter what the schematic is. You can go to File and save as Python code, and this will save the whole schematic as code, right? And then when you open this code and you run it from VS Code, for example, then this will build a schematic, a PSIM schematic. So this will build the original schematic. Now, why this is useful? First of all, for version control, you can save your schematics and push them to a Git repository and work with changes. And you can also do other nice stuff like trying to generating PSIM schematic with Python code using AI chatbots. Like you can have ChatGPT or any other AI chatbot mentioned to the bot what are the different functions of the PSIM API, and then you can try automatically creating schematic by letting the chat know what you want to do, what topology you want to do. This is really fun, and I really want you to try it. And finally, I want to show you an example with an efficiency map. So this is part of an example with Python. This is part of an example that is uploaded in our community. You can directly do it from scratch by yourself. So you can go to the Altair community and look for this example, generating efficiency contour maps for redrives using PSIM and Python. This includes a step-by-step guide on how to do this. It includes 3 different Python scripts to help you get there. And let me now explain what these scripts do. First, you have to have your schematic ready. You can see here that I'm using the steady state function because I want each point, torque speed point, to reach steady state. Then I have a Python script that samples the torque speed envelope and saves the torque speed combination of points in an Excel file. Then I have a second Python script that opens this Excel file and is calling a PSIM simulation to run these points to steady state. And then it gathers all the steady state results in another Excel. And then I'm having a third Python script that reads this second Excel, which has speed, torque, and the third column, which is efficiency, and lets you graphically create the contour. So this is an end-to-end process of how to create an efficiency map with Python, which you can find online in our community. And this leverages the multi-thread PSIM function, which will be fixed in the next version. So right now it will only run consecutive, which will only do consecutive PSIM calls. Now, let's say that one of your operating points didn't achieve steady state effectively, or you see some weird results. This would ruin your contour map in here, and then debugging wouldn't be so easy. You would have to go to find this specific point, open it, see what is wrong, and so on. So for that reason and many more, we also developed another solution which involves using a code-free platform for design exploration and automating your power electronics simulation, which involves the combination of PSIM and HyperStudy. So HyperStudy is another tool from Altair, which is specifically designed to do that. And the connection to HyperStudy is one of our, let's say, 4 core pillars when it comes to PSIM simulation, because it covers this design space, exploration space, and everyone is interested about this. Everyone wants to check the limits of their design space, apply optimization routines, build reduced order models with PSIM trained data. So this is something that is really useful. And then there are also other things that we're trying to integrate PSIM with from the Altair portfolio and hopefully from the Siemens portfolio as well soon for the thermal analysis of the inverter, like 3D thermals and CFD, and also the system design, including reduced order models of motor designs coming from a finite element tool, working with complex mechanical loads coming from a multi-body dynamics tool. So this portfolio of Altair has enabled all these different workflows that someone can do right now with PSIM. Focusing on HyperStudy now, HyperStudy can be used, let's put it simply, for one of the following 3 things. The first one is exploring the design space. I also mentioned design and market space because you can include price data and you can use lists from your suppliers, including price as well. So the way this works is you load a simulation, you build a bunch of, you run a bunch of examples, and this will be your design space. You can put limits on it, you can put some constraints on it, and you can visualize the results. You can post-process it with data analytics tools inside HyperStudy, but it's you, the engineer, that sees the results and interprets them. Then the second thing you can do is an optimization and coming up with a Pareto front of your design. This is a bit different from the DOE because you, again, load the PSIM simulation, you define what are the variables and what are your key performance indicators, for example, efficiency, cost, EMI, whatever. And then you let HyperStudy apply an optimization routine. And then it automatically checks or rather creates new examples with new inputs based on the results of the previous outputs. So it starts with some random inputs. It analyzes internally some trends, and then it guides by itself the way of the inputs in order to hit your optimization goals and give you the Pareto front, which is the list of the optimized trade-offs in a multi-objective optimization problem. And finally, you can do static reduced order models, or fit models as we call them, and using the results of your DOEs. So the DOEs are very good at generating PSIM results, and then you can use fit models in order to create a reduced order model out of this result. So looking back at the efficiency map example, so we created a contour in the previous slides of the efficiency map. But what if you want to change the semiconductor or the switching frequency or the modulation technique? Then for the same torque speed envelope, this would result in a different 2D plane for each semiconductor option, for each switching frequency option, and so on. So the actual design space is not a 2D graph. It's actually multidimensional. And this is where the HyperStudy DOEs and fit models help. So this is a fit model that lets you know the losses of a traction inverter in the torque and speed envelope. So x-axis is torque, y-axis is speed, z-axis is losses. But you also have drop-down menus and sliders that helps you iterate and see how the losses change between these system options. So the blue dots you see in the screen are the results of the DOE. So they are basically PSIM outputs. And the curve that you see is fitted between those blue dots is actually the fit model. So HyperStudy uses the results of the DOE in order to create a curve, a 3D curve, that captures the losses of the inverter. And this can be deployed in 1D as well, or it can be saved as an Excel file. This means that you can deploy it somewhere in 1D, and you can say, for this speed, for this torque, for this semiconductor, for this case temperature, for example, and for this gate resistance, what is the losses? And the fit model will tell you what is the losses, which is very useful for drive cycle simulations, for example, or exploring system trade-offs in a large scale. So this is one of the things HyperStudy can do. Now, the way this works, and let me stop it there. This is HyperStudy. This is the platform of HyperStudy. Of course, I will open it live, but I wanted to give you a few seconds to scan the tutorial if you want to see the step-by-step guide on how to connect PSIM with HyperStudy. The way this works is that you open the platform of HyperStudy, and then you add a model. HyperStudy is not limited to PSIM. You can add a model from other multi-physics tools of Altair, like Flux, FICO, SimLab, to do low-frequency electromagnetics, high-frequency electromagnetics, thermal, and also solvers from other vendors as well, but that would require some tinkering from your side. The Altair tools are already there for you to use them. And then you select the tool, in this case PSIM, and you just navigate to the schematic. So you navigate to the schematic, and then you click import variables. And that's it. Then all the variables of inside the schematic that are parameterized inside the schematic will appear here. And not only variables such as the PWM technique, the switch used, the dead time, switching frequency, you also get the solver variables, like the total time and the time step, which means that the time step can be a function of your switching frequency when it comes to exploring different switching frequencies, which makes the study even faster. And now, what is the benefits of this approach is that everything happens in a very structured way. The handling of inputs, outputs is it's always the same. It's a very structured approach, GUI based, so no code is written. You can put lower bounds, upper bounds, modes of discrete or continuous variables. You can put statistical distributions and tolerances when it comes to certain components. And all of this is graphical, which means that, for example, if you try to do that with scripting, and as a manager, you give this task to 10 different engineers, you will end up with 10 different scripts because each mind works differently. And even though it's always Python or it's always Compose, each person will do things slightly differently, and another person will have to read the script and understand what is done. And even the same person, if it reads the script 1 year later, they will not be able to understand exactly what they did so easily. Also, if something goes wrong, then the engineer will not be able to find or debug the process directly unless they are very careful on how they handle the outputs. If they save the example in a different file each time with a different name, then yes, maybe. But what about the data analytics? Then you also have to write your own scripts to visualize the results, to build the scatter plots, to build the contours. All of this happens. All of this is integrated inside HyperStudy, and you don't need to script for any of that stuff. So if you open your study 1 year from later, it will be exactly the same. If you give 10 different people the task of generating an efficiency map of HyperStudy, you will find that it will be exactly the same study. So everyone in the team will be able to understand what the other person did and even what they did in the past. Now, a classic example is again with a motor drive. You can take the motor drive, you can discretize the torch feed envelope, and you can have HyperStudy run the simulation to steady state for each example. But what if you want to calculate things like the settling time or the rise time or the overshoot of your torque and speed? Then you would need to write your own functions. And of course, you can do that. So you can still use your Python and Compose functions inside HyperStudy if you want to post-process things your way. But the meaningless labor of handling inputs and outputs and generating simple graphs and data analytics, this is all covered by the tool. So it's a combination of you having a tool that saves time from you to handle all the things that you know that you can do with scripting, but you don't really want to sometimes, and still lets you create your own functions and apply them on the results. Typical graphs you will get out of HyperStudy are these linear effect plots. For example, this plot gather all the results and categorize them and lets you know the trends of your system. For example, for this particular drive, I understood that, okay, after the torque, what affected the efficiency the most was the switching frequency, the semiconductor selection by 35%. Switching frequency was 17%. So this is useful to know in case you can, for example, change the switching frequency instead of changing the switch. Then other things you can do is optimization. We already done a webinar for the cost-aware optimization of a second stage filter. Basically, you can put goals like the switching frequency attenuation and phase margin. HyperStudy will run several simulations. It can also run frequency domain, as you can see here. And you can iterate between each result. So you can actually see it inside HyperStudy and see what is wrong and directly open it and fix it from the GUI. And then you can also include other files like Excel files, or you can connect a Python API from your supplier inside HyperStudy to bring in the price of your filter components, for example. And this will enable you to build contours like that. So here we have two conflicting goals, which is the filter attenuation and the phase margin. And then we also have the price all gathered into one contour. So we see this blue spot here. This has a high filter attenuation and acceptable phase margin. Blue means it's cheap. So obviously, if I was an engineer, I would select, I think this is a capacitance, I would select the capacitance to be inside this region of my design and market space. And finally, what is very, very important is that HyperStudy can also act as, the orchestrator for tool chaining. So you can add a PSIM project, then you can couple it with the outputs, inputs of a Flux project if you have a motor design or a transformer design, and you want to calculate the core losses in a high-power transformer with finite elements, for example. And you can also use SimLab, which is used for NVH analysis, and it's actually a multi-physics. It has multi-physics solvers. You can also do CFD, you can do thermals, and so on. Now, I will, in the minutes that we have left, I will quickly open HyperStudy and show you how to load a schematic, how to change the components inside the schematic and iterate between them, how to define your own functions, either Python or OML, and how to explore your results in the post-process menus. Now, I want you to be careful of two things when you use HyperStudy. First of all, or rather three things. First of all, please make sure to watch the tutorial. We have take quite a lot of time to capture every step of the process into the tutorial, which was shown a few minutes earlier in the previous slides, because it's a strict environment, and before trying to do anything your own, I think it will be very helpful to see all the steps with a simple example. Then please be careful of the file paths, of the names of the file paths. So special characters in the file path will not work, or too long, or a too long path name will also create problem. And finally, please don't use OneDrive or cloud-connected folders for your studies. So if you want to have a simulation and run a study on it, make sure this is in your C drive or your local drive, because the constant updates of the drive of the cloud-based folders can create problems. Now, I will now open HyperStudy. So this is the platform, and I will open the same back converter example, or a similar back converter example, which has a parameter file in it. Maybe I can directly open it from inside PSIM. One second. Okay, here it is. And then there is a parameter file where I'm having some parameters. L, C, switching frequency, output power, and so on. Now, I can create a new study. Click Add Model, click PSIM, load the same schematic. Click Import Variables. And once you click Import Variables, a new window appears that lets you know all the variables of the simulation. This window is in my other screen, so let me bring this here. And then all of these variables are in your plate to use. You click Export to HyperStudy, you click Next, and you have them. You can put lower bounds, upper bounds. You can have them to be continuous or discrete. They can follow a tolerance distribution. You can create constraints, and you can create links with each other. Let me rename the actual var names here. And in the links, what is very helpful is to define the time step as to be 1 divided by switching frequency divided by 50, for example, to use always 50 points per cycle, no matter what your switching frequency is. I will click Next, and then I will run the definition. Once you click Run Definition, high-fidelity calls PSIM, and it executes things once. Now, I have already done this, so I'm not going to wait for this. I will directly open the result. So when this is done and all the green arrows are blue, sorry, or all the arrows here are green, you can post-process the results. And the way this works is that you load the files that are being generated. They have this .abf format, and this is in order to be low in space in your computer, so they are binary. These are waveforms. So this is the current, this is the output voltage, and then you can post-process these waveforms with your own functions. For example, I have a DC component function inside Compose, which I can directly right-click and register function to HyperStudy, and this will enable me to use this function inside HyperStudy in order to post-process the results and see the actual output value at the end. And then you build a DOE, you select how many runs you want, you select how you uniformly distribute the points, and that's it. You let HyperStudy run all these different simulations. You can use a multi-thread approach. You can define how many jobs you want to run in parallel. And then for the post-processing, you have access to the complete list of data sources for which you can use how the waveform looks like. And if you don't like something, you can see the index 33. So you can go to index 33 and click Show on Explorer, and this will open the run 33. Every result is being saved in a different file. You can open it and see what is wrong. There are like linear effects that you can investigate. There are Pareto fronts, which you can use to investigate what affects the system the most, like what affects the DC component the most, switching frequency, and so on. So there are the multiple things you can do here. So this is what HyperStudy can do. Please find the tutorial and see the step-by-step guide on how to do this by your own. I will close this webinar by having these final comments as the final slide. When it comes to the PSIM automatic methods, there are 3 scripting approaches. For these approaches, it's hands on keyboard and sky is the limit. Basically, you can script whatever you want, and you are limited only to your imagination. AI chatbots are evolving rapidly. I'm really curious what you see if you try to use an LLM to produce Python code that creates a PSIM schematic. And for the script-free approach, there is HyperStudy, and its advantages are that it's a very robust and GUI-based automation solution. You don't have to be very skilled with scripting in order to use it, but you can still use your custom scripts if you want to. So just take the fun part of scripting. So this leads to time saving as it removes the inefficiencies of having to script inputs outputs. It leads to improved data post-processing, and it's a consistent time investment because the time required to learn the tool will be once, and then it remains the same regardless the complexity of what you can do. So it is very easily reproducible. So that's it for today. Thank you for attending this webinar. I would be happy to hear your questions if you have any. Otherwise, see you in the next one. I don't see any questions in the chat. I'm not sure if this is because I'm a presenter and not the organizer.
Hey, Nikos. Yeah, I don't see any questions in the chat either. So we'll just wait, give a couple minutes for folks to think, and then we can close off. Otherwise, thank you for your presentation.
Thank you, Albert. Thank you, everyone, for your time.
Yeah. Yeah, lots of little thumbs ups and clapping hands. So people are acknowledging that the presentation is finished. Just no real questions, it looks like. So obviously a clear indication of a job well done, I hope. We are available for questions if you do have them after the fact. You should get, as you sign out of the session, you'll be prompted for some feedback, and you can fill in the questions there, and we will get those questions as well. So do feel free to submit questions through the exit survey, and we'll answer them there too. We have your contact information. We can get back to you. Okay, Nikos, I think you're off the hook for questions. We'll close the session, and thank you so much.
Thank you. See you in the next one.